And if you like, Sean, I can share the poll results if you like, if I
Yeah,
want to
yeah,
go
let's
back
do it.
to.
It'll be a good
So
segue, I think.
yeah, these are the questions I've got on the screen. I'll end the poll if I can. Let me. Here we go. Where is it? The poll. I actually don't have to end it at all, but if I do, I think people won't be able to respond. Last chances. So question one. The answer 61% said yes, 39% have said no. Question number two, do you know how to read hydraulic capture inlet charts for sag and on-grade pits? It's basically half. 46% said yes, 54% said no. Question number three, have you used on-grade field inlets on inverted roads? 41% said yes, 59% said no. Question number four, 16% said yes, 84% said no. Do you undertake sensitivity analyses, etc.? 42% said yes, 58% said no. Question six, do you know how to assess tailwater conditions? 36% said yes, 64% said no. And the last question, do you undertake hand calculations, etc.? 36% said yes, 64% said no. Cool.
Interesting. Yeah,
Interesting.
good
So
insight. Yeah,
I think I
excellent.
can share those results if you can see them. I'm not sure how that appears at your end. But look, without further ado, I might pass it over to my esteemed collaborator in Sean Quilty. Everyone who attended the first one is familiar with how amazing he is, knows his stuff. Director of Quilty Engineering Hub, associate principal, I believe, at ADG Engineers, and has been lecturing at TAFE Queensland for over 9 years now, and just loves talking about stormwater and loves teaching. And we're very privileged to have him here today. So again, if
Thanks,
you've got
Brad.
any further questions for Sean or questions you'd like to ask him, please put them in the Q&A. But Sean, with if you like, you're welcome to share your screen.
Let's do it.
Let's do it. And thanks for everyone for dialing in. I can see it's just about to tip over 400 in attendance, and a big thank you to Sean for giving up his time today.
Of course, pleasure, Brad. And you've you hit the nail on the head. I just love talking about stormwater and everything civil engineering. So, all right, we'll get stuck into it. Now, I am going to be wary of time. I know I ran over time last time, so I do have a little bit of a timer here just watching me. All right, so we looked at the rational methods last time, so hopefully everyone's pretty comfortable with that now. And so now we're going to see what we can do with the rational method. And one of those things is actually designing and sizing stormwater inlets. So how do we get the water from the ground and push it into our pipe system underground? So again, I'm going to use one of my favorite guidelines. There's a couple extracts in here, a couple tables, and it does come from Putum. Widely adopted throughout Queensland. It's pretty much the stormwater sort of go-to manual. But there's a lot of stuff in there that does apply to all states and territories. It's just stormwater focused, not necessarily Queensland focused. So if you do get a chance to pick up a copy, definitely have a read through. If you're not sure about anything, always get in touch as well. I've always told everyone my door's open. You can send me an email or message via LinkedIn. If you're stuck on a project, you just don't know what to do, just flick it through and we'll see if we can help you out. So today we're going to first look at the terminology of inlets, just explain some of the key sort of words, because it does vary slightly. And especially if you start working in different states and territories, we try to, or we like to use some different names. We're then going to go into the flow limits. So before you actually size and design a stormwater inlet, you've got to understand how much water is actually heading towards that inlet. Then we'll talk about some flow terminology. So there's different, I guess, types of flows, if it's approaching the pit, if it's going in the pit, and so on. And then finally, we'll look at how we can read inlet charts. And hopefully I come bang on time and we'll have heaps of time for questions at the end as well. All right. So what we're going to be focusing on today is all about stormwater inlets, but it's really focused on urban environments. So where you've got your typical roads with your kerb and channel, Typically when we get into those urban environments, they're really densely populated. So you'll have subdivisions, you can have, sort of CBD, really heavily populated areas. And that comes with a few, I guess, constraints. So spatially, we don't have a lot of room. So we've got to try and manage flooding within a really small amount of space. Everything's just jammed in. We've got a lot of vehicle movement. So we need to think about how people can actually drive safely through rain events and through flooding events as well. And we've got a lot of pedestrians moving around as well. So if you think of your typical subdivision, there's going to be kids playing, especially when it rains. They just love to get out there. In CBDs, you've got a lot of movement. You've got public transport with just hundreds and thousands of people moving around. So they're the sort of things that we're dealing with in an urban environment. So then when we think about flooding in an urban environment, we have to think about pretty much every storm. So if we look back to the Rational Method webinar that we had, or my free online course about rainfall, we look at frequent, infrequent, and all the way up to rare events. So that's about how likely am I going to have one of these storms occurring. And so we've got to look at this full spectrum and try to work out a solution. So this is where we look at convenience. So if we have really frequent events that's going to occur multiple times in a year, we need to make sure that people are I guess it's a convenient place to live, right? So you're not constantly stepping in puddles or streams of water running in front of your footpaths. But then when you get into infrequent events, more heavier rainfall and larger sort of flooding events, we start to look at more focus on the safety aspects. So we don't want people to get washed off of their feet or cars to be washed off of the road. And then we look at property as well. We don't want anyone's house to flood. We don't want any buildings in the CBD to become flooded. So that's kind of what we're dealing with when we look at urban environments. So how do we solve this? Well, this is where longitudinal drainage comes into it. Now, longitudinal drainage is kind of the technical term, but you'll hear in the industry probably more often pit and pipe. So if you're looking at a pit and pipe design or a pit and pipe system, this is what we're talking about. So this is a combination of stormwater inlets that are connected with a series of underground pipes. And it's all a gravity-based system. So it relies on these pipes to be laid on a grade. So all that water will just flow under its own gravity and empty out. So these systems are designed typically to be free draining. Once the rainfall event's finished, then all these pipes drain out and they're dry, ready for the next event. So the majority of pit and pipe systems in Australia pretty much discharge to either a creek, a river, or an ocean. Or if we go inland, there might be some decent sized dams, but it's pretty much free draining for the majority of Australian environments. So this is where we use longitudinal drainage. We need to reduce the flooding. So what we try to do is we want to transfer all of that flow that's happening above the ground, on the road, on the footpaths. We want to push all of that water into the ground. So we've got to somehow transfer that through. And that's where we get these inlet structures or inlet pits to actually let that water drop underground and then discharge through a series of pipes. So you can see in this image here, there's a pretty wide flooded width. And then as it comes down the road, you can see if that catchment got larger and more water tipped out onto that road, that flooded width just gets wider and wider and wider until eventually it becomes unsafe or inconvenient or a risk to people driving on the road. And you can just see a little bit in the sort of mid area of that photo, we've got an inlet pit, and you can see all of that water basically just funnels and then drops in. So there's virtually no flooded width downstream of that. And that's what we're going to look at in a bit more detail. And it's a little bit hard to see, but if you look at the next pit further downstream at the background of that image, you'll see the flooded width now starts to sort of widen again until it drops into the next pit. So they work really well, but you've got to be a little bit clever about where you put these inlet pits. And so where we place them are based on some calculations and also some flood estimation. And again, that's where the rational method comes into it. That's typically what we'll use for pit and pipe design. We need to provide convenience, we need to provide safety, and we need to reduce the risk to the community when these flooding events occur. And more, I guess the spotlight's been shone a little bit more on this, but I think it's always been important. We need to see how we can reuse this water as well. You can imagine in that image there, all of that water is just funneling and dropping into that pit. That's beautiful, clean water that's fell from the sky. And now it's just conveyed into the pit, and eventually it will just head straight out into the ocean, typically. So all that water is just being wasted. And we know we can reuse that for drinking water, for irrigation, for lots of things. So when we look at stormwater inlets, typically there's two classifications. You can have a stormwater inlet that is in a sag position, and we'll call that a sag inlet, or you can have an inlet on grade. So essentially what we're looking at is in a sag pit, your water is going to come from both directions. So your topography, your ground is actually coming down into a low point. And so then that water is just going to sit there and pond. And that's where we'll have a stormwater pit to allow that water to go into a sag inlet. The picture on the bottom shows an on-grade pit. So you've got a road that is on grade, and then if you put a pit there, the water is going to run down that road, drop into the pit, but it's going to continue on. If there's enough water, it will actually bypass, and you won't capture all of that water. And we'll touch on that in a bit more detail soon. So they're the two things that we're going to look at today: sag pits and on-grade pits. Now, there's lots of different names that we use for these things. We can call them inlets. We can call them pits. They're called gully pits, especially in southeast Queensland. And then we're going to look at another type, which is a field inlet, but they can also be called drop inlets. And if you head up north into the Northern Territory, you'll start using what we call side entry pits. And elsewhere in Australia, you might call them kerb openings. So it's essentially looking at that kerb. It's just basically the kerb opening up and allowing water to spill in. Heaps of different names, but they all mean the same thing. We're trying to get water from the top of the surface and drive it into some pipes. So we did talk about storm frequency last time. So how likely is a particular storm going to occur in any given year? We can split up this storm frequency into two classes. We can look at minor storms and major storms. So typically your minor storms, so these storms are going to occur more frequently. That's where we will look at implementing underground flow. So our pit and pipe design to push that water under the ground. But we can only do that for minor storms, because the more water that you get, if those floods become bigger, then your infrastructure, your pipe sizes, your inlets have to be much, much larger. And so there comes a point where it doesn't become practical or feasible. You won't be able to afford or even fit the infrastructure in your space that you have. So it's a bit of a balance of how much water you can actually capture. Then when it comes to the major flow, that's where we're looking at the very rare events, infrequent events, but they're a massive amount of water that's going to be flowing through our roads and our properties. So that's where the pit and pipe design basically becomes completely full and over capacity, and it will start to bubble up and surcharge. And that's where we try to push all of that water into an overland flow scenario. So we'll allow all that major flow to actually run through your road corridor or add larger drains and open channels and drainage reserves to get rid of that water. I've got a couple of tables there. I'm not going to go through it in detail, but if we have time at the end, I'm more than happy to talk to it in a bit more detail. But it basically just shows you different types of development categories and what AEP or storm frequency you should be applying for that design. So that gives us a starting point of how we're going to design and what, I guess, what target we're going to look at for capturing that water. Okay, so we've got kerb inlets. And these are three different pictures, but they're all a kerb inlet. It's an inlet that is basically positioned on a kerb. The top one there is a side entry pit. So this is what we use up in Darwin, for example. One of my favorite places to work. I've had a lot of really cool, interesting jobs up there. We've also got grated inlets, which is the middle image. And you can see there is no kerb opening. It's just a grate. And then down the bottom, we call these combination inlets. but the more common term that we use is a gully pit. And that's a combination of your kerb opening plus your grate. So let's look at some of this terminology. In a kerb inlet, typically you're going to have the actual kerb opening, and water will be able to spill in. You'll have a lintel, which is a structural reinforced bit of concrete that will actually withstand any wheels that might park on top of it or drive on top of it, and keeps that shape. Now, in that kerb opening, it will actually come into the kerb and then it drops into this trough. And that trough is like a little internal channel that just funnels that water into our chamber. We have our grate. And then we've got the physical chamber underneath. Now, this is just basically a nice big concrete box, essentially. So that water just drops in. And then out of that chamber, we will have any stormwater pipes to connect and discharge that water elsewhere. And we also have these kerb transitions. So typically the kerb itself, upstream and downstream of the pit, will be constructed using a kerb machine. They'll form that kerb and then they'll stop about 1 meter to 2 meters before the actual kerb itself, give a bit of space for people to work on and construct the pits, and then somebody will come in and hand form that last transition between the kerb and your lintel itself. So they're pretty much all the elements that you'll find in a kerb inlet. We then have field inlets, or in some areas we'll call them drop inlets. Now, typically these field inlets are positioned in a sag. So these are a sag pit type. So it's in a low point, and as the name suggests, usually it's out in the field. So it might be in a park area or a vegetated sort of area, grass, plants, and what have you. And usually we've got 3 different types of field inlets. So we have a flush mounted grate, which is the top left. So that grate is flush with the surface around. We have an elevated grate, which is the top right. So there's actually a bit of a gap, probably about 90 to 100 mil gap from the surface to the top of the grate. And then we have these dome screens in the bottom left. So each of them serve a different function, and they've got pros and cons for why you would use one over the other. And yes, a little tip, these things need to be maintained. You can see in the top right there, that was a picture that I took shortly after a storm event. And you can see all of that leaf and litter debris has washed down into this pit and basically just sat on and around. A lot of that debris probably went into the pit and then out to the nearest creek, but there's a lot that's sitting on the top. So when the next storm happens and all that water comes rushing down again, you're basically blocking majority of your pit. And so it's not going to function the way that we want it to when we design it. And blockage factors are a major concern and something that we need to understand and calculate correctly. So keep that in mind. Your pit and pipe design is only as good as how much you maintain it. So with our field inlet, we've got our grate. So the water just basically ponds in here because it's a sag, and it'll just drop into that grate. We can have a concrete apron around there as well. And they tend to be quite good because you'll have, grass or in here vegetation, and it's very easy for all of that vegetation to actually grow over the grate, and that can cause blockage as well. Whereas this concrete apron gives you a bit of a buffer or separation. So it reduces the chance of some of that blockage. It's also handy for maintenance crew because they'll spot it, a few hundred meters away. It's very easy to see. And similar to the other pits we were looking at, underneath that grate, we've got a chamber or a box, and the water drops in, and then we have our outgoing pipes. All right. So we kind of understand what these inlets look like, all the different components, and really their job is to just get the water from the surface and push it down into some pipes to discharge somewhere else. Now, the next thing that we need to look at are the limitations or the benchmarks or guidelines we have to look at. And this is where flow limits come into it. So before we design a pit and we position an inlet pit and we decide how big that pit's going to be, we need to understand what type of flow or how much flow is approaching that particular pit, and that will allow us to size it. So to do that, we jump onto the rational method, we look at our catchment, and we'll calculate for a particular storm frequency how much water or what discharge rate will be approaching the pit. So a few things that we need to consider. First, we need to calculate the approaching flow, but we need to ensure that that flow width is a certain acceptable width. So you can see that water there is kind of widening out almost to the line marking. So how wide can we actually go? Can we go a little bit into the track of a car? Can we go right up to the crown? Can we just submerge the whole lot? They're the sort of things we need to look at. We also need to look at flow depth and ponding depth as well. So if we have a sag pit and it's in a low point, your road sort of comes down here, how deep can we allow that to actually pond up until it becomes unsafe? And then we have another term, which if you're new to stormwater design and pit and pipe, you will hear depth velocity product or the DV product. And what this does is it takes the depth of the flow multiplied by how fast that flow is running down, and you get a certain number. And then in our guidelines, we'll give you a limit of what you can push up to that sort of point, and then after that, it becomes unsafe. So the depth velocity product or the DV product, if you can imagine a cross section, you've basically got a width or a cross-sectional area of water that's heading down the road, say, and that'll be heading down at a certain velocity. So you've got this wall of water or momentum that's pushing down. If your flow depth is really shallow, but it's heading down really fast, it's not going to knock you over. If it's really, really deep, but it's flowing very slowly, it's probably not going to knock you over either. But if you get a combination where it's fast enough and deep enough, it's actually got the potential to knock small children over or anyone that's vulnerable, I suppose. And that's what we've got to look out for. And that's the DV product, and probably one of the more important things to look out for. And from what I've seen in the industry, sometimes it is missed. So when we look at these flow limits, we've got to think about the vehicles. So is it safe for a vehicle to, in this case, it's a parking lane, but if that flow width was to flow into our travel lane, what's the limit and where does it become unsafe? So we think about the vehicles, and we also think about pedestrians. So at a bus stop, we've got to think about people trying to get on and off of a bus, and how wide can we have that flow? Similar, we look at pedestrian crossings as well. So if you're going to cross a road, there's a good chance water's going to be running down that road. So how wide can you go before it becomes inconvenient is one thing, but then also unsafe. So I'm not going to go through this in a great detail, but now that you have the webinar and you'll get recordings, you'll be able to see these and reference to them pretty quickly. But typically, if you're looking at just some thumbsuck sort of values that you want to remember or just keep in mind, generally, if you've got like a typical subdivision, a minor sort of road, not a lot of traffic, in a minor event, you're allowed to flood or allow flooding up to the crown of the road, which is pretty, not extreme, but that's a lot of water that'll be flowing down the road to that point. But when you get to an intersection, you don't want that whole width of maybe 2.5, 3 meters of water running down that intersection, because there's a good chance it's just going to flow over the intersection and cause flooding and unsafe driving environment. So there, we need to get that flooded width and actually reduce it right down to 1 meter. And so the way that we do that is by incorporating more inlet pits. Another thing to keep in mind is when you have pedestrians, so crossings or bus stops, it's usually about 450 millimeters is the widest you can have as a flooded width, which if you need to think about it, just think about a nice big step. If you can physically step over that flooded width, then you're on the right track for a minor event. This next table here the previous one was talking about longitudinal flow, so flow running parallel with the road. This one here is for minor events, but for transverse flow. So if water was actually overtopping the road and going across perpendicular to your road. And the top one, which is probably a good one to remember as well, is still water at a road sag. So if you've got a field inlet that's in a sag or a gully pit that's in a sag, typically you want to keep that ponding depth below 300 millimeters. So just some nice numbers to kind of keep in the back of your mind to look at for your next design. We then get into major storms. And so I said before, with pit and pipe design, you typically break it up into minor storms and major storms. And they're the calculations that you will run. So again, I'm not going to run through this, but if you need to have a takeaway for major storms, if you're looking at flow that's running down the road, so it's running parallel to the road, if you keep your major flows below or at the top of kerb, generally you're okay. And obviously there's heaps of scenarios where you kind of go a little bit more, but typically if I'm doing a concept design, I will jump in and just assess based on top of kerb, and I know I'm going to be right for pretty much most scenarios. And then again, when we look at transverse flow, so water that's flowing perpendicular to your road, we've got a similar limit, if you like, for a major storm, where in that sag, you can still only pond up to 300 mil. And you also look at a DV product. So if you imagine your road's heading down and your car's driving down there, but then you get a flow that's coming at right angles, it's going to want to push your car over. And anyone watching the news the last couple of months, you would have seen, for example, on the Gold Coast, a lot of footage of cars actually getting knocked over and washed away at floodways. And that's all based on a DV product, that depth velocity product. I can't keep going on about that. I would love to, but I'm just watching time, so I'm going to keep going ahead. So when we look at this approaching flow, or looking at these limits that we've got to comply with, one of the things we need to do is estimate how much water is running down that road, or what's acceptable. And this becomes a bit tricky because you're going to have all sorts of road grades, all sorts of configurations of roads, your crossfall, your width, different kerb types. But what we do have is one equation that we can use, which is Izard's equation. So if you haven't heard of that, definitely take a note. It looks complex there, but it really isn't. It's basically just a bit of a rehash of the Manning's equation for triangular section. So this is what we use to assess that approach flow and see if it's safe. And the way that you can do that is by creating a spreadsheet, maybe something like this, where you basically have, and I don't expect everyone to read this, but on the left, you'll have your road grade all the way down. So 0.5% grade, 1%, and you just filter right down. And then as you go across the table, you can have varying depths of flow. So the first column is 30 mil deep of flow. The next is 40 mil, 50 mil, until you go all the way up until the road's full and over capacity. So if you have a table like this, it's really easy to look up. You calculate your approach flow, and then you read off of this table, and then that will tell you if you had, say, 300 liters a second heading down your road, you can look at this table and then quickly see how wide that flooded width is, what the DV product is, and then what you can also do in here on the right-hand side, so this is a spreadsheet that we create here at Quilty Enginering Hub. I put in a DV limit and a flooded width limit. And then on my spreadsheet, anything that turns red basically shows me that that's unsafe, or it's the flooded width is too wide, or the flow is actually overtopping the crown. So it's a nice good lookup that you can use. Now, QDM, in the back of the QDM manual, they've got a few tables exactly like this. But this spreadsheet allows you to change the kerb types, the flooded width, the road widths and crossfalls and configurations. So you can do something like that. Now, we do have an Inlet Design online course that's going to be live in the next few days. And when you enroll in that course, you do get this spreadsheet for free as well. So if you're interested, or if you want to ask any questions, definitely get in touch with me and we can talk a bit more about that. Okay. So we know we have inlets. We need to push that water underground And now we know that there's limitations that will help us figure out how many inlets we need or where we need to put those inlets. So now we look at some flow terminology. So Q being the flow rate based on our rational method calculations. We know that that terminology, or that the letter Q is basically peak flow. But we can then split that up further and say that we have a catchment flow, an approach flow, an inflow, and a bypass flow. And if you're doing pit and pipe design, you need to understand this and quite well as well. So one of the first things that we need to do is understand our catchment. We can understand the topography by obtaining contours, survey data, site visits. There's a lot of things that we can do to actually understand where the road and the lots all fall. That's our first thing that we need to be able to do, really understand your catchment. Once you've done that, you can then understand how the road falls or grades, and then you know any inlet pit that you put on those roads that are falling in one direction will be on grade pits. You can also identify where the road has low points, and so that will be a sag location. So you'll need sag pits in those locations. And with that topography, you'll also understand how those lots will be able to grade. Are they grading to the road, or are they grading away from the road? And that obviously affects how much water or runoff will head towards certain pits. So here you might look at it, you might have some contours, and you might identify that there's a crest somewhere in your road. And at the intersection, this intersection might be at a high point, and so the flows might actually divert in both directions. So you've got to understand what's happening on your site first. So when we understand that, we can then see where are these lots all going to grade. So we might have a series of lots grading towards the road, adding more flow to the road, or grading away, and then you've got a heap of flow in the back of your property. We can then look at our road crests. And we know that when we have a crest or a high point in the road, it's going to push water in opposite directions. And so when we have a typical two-way road or two-way crossfall on our road, we then know that the water is going to split and then head to the curb on either side. And then those curbs are going to direct flow down the road. And then when you get to an intersection and you have curb returns, it will direct flow around your intersections as well. So this is where that understanding needs to come into it. You've got to really know what your catchment's doing. So an example here, if we had a road coming towards us, grading down towards us, and then grading towards the right, we know that the flow is going to run along that intersection and head down there. So we understand where the flow is going to go, and then we can calculate how much flow there is and if it's acceptable, or if we need to cut off that flow with an inlet pit. So we'll look at this terminology. We will first look at catchment flow. So let's say we have some inlet pits here and then a pipe system. Let's look at this single inlet pit here. This will have a certain catchment. And so the flow approaching that inlet will be our catchment flow. Similarly, if we have another inlet on the other side of the road, we can calculate what that catchment is, and then that's the catchment flow. We then look at the inflow. So we know the water approaching the inlet pit. So we saw that that was going to be our catchment flow. And in this case, we could call it the approach flow. And I'll show you the difference in a couple of slides. So you've got this flow approaching the inlet. Then you're going to have some of the flow, maybe all of the flow, depends on how much, going into the inlet. And that's what we call inflow, or QI. Now, if there's too much water heading towards that pit and the pit can't capture all of that water, you're going to be left with a small amount or a lesser amount of water. And that's what we call bypass flow. So if you're on grade and your road is on a constant grade and you have your field inlet, you will have some of that water that will bypass if there's enough water approaching. So if we have an inlet and it's at the top of the catchment, our approach flow is equal to our catchment flow. There's nothing else really heading towards that inlet except for that catchment flow. So that's for that particular inlet. Now, as that flow approaches this inlet, it will be captured by the inlet itself. But if there's too much flow, you will be left with some of this bypass flow. If we look at the pit further downstream, we have a catchment that's heading towards that inlet pit, and we can calculate that. But our approach flow is going to be our catchment flow plus that upstream bypass flow, because we've got additional flow that's spilling or bypassing that upstream inlet. So just keep that in mind as well. Your approach flow needs to account for any upstream bypass flow. All right, so there's our terminology. Now we're going to look at inlet capture charts. So at this stage, you'll understand how to calculate your peak flows first using the rational method. You would analyze your catchment. So where's the water all going to fall? And then you can start to position your inlet pits at trial, if you like, trial locations, or just a bit of a guess, an educated guess of where you need the on-grade pits. And you definitely need them in the sag points as well. And then once you've got those locations, you can then confirm or finalize your catchments, the area and the Q value that's heading towards those inlet pits. You can assess your flow limits to make sure the flow approaching is not too wide, too deep, or the DV product's not too much. Once we're at that stage, we can then use inlet charts, which are based on mathematical equations, and we can look up for each specific inlet pit, you would have a specific inlet chart. So it will say for that particular pit, if you had a certain amount of flow approaching it, it will capture X amount. And that's what we really need. And that's something that a lot of people don't realize. If you're doing pit and pipe design, you must be across the inlet charts that are used. And that's something that is missed. Sometimes it's relied upon on the software, and you just pick a pit and then you let the software crunch the numbers. But really, you want to be able to break down those calculations and really assess and understand what's being used in that space. So those inlet pits, I skipped ahead there, sorry, but those inlet pits, move back, they can be based on mathematical equations, or they can be based on laboratory testing. So this image here is from the University of South Australia, where they basically constructed a life-size scale model of inlet pits and road cross sections, and they actually have it on hydraulic pistons, and they can actually lift the road up at different grades with a flume, apply a certain amount of water running through, and they can calculate how much water each of these inlet types are going to capture. So when we're in a sag condition, what we call the hydraulic performance, which is basically how much water will this pit be able to capture and push down underground. In a sag location, the performance is based on the ponding depth above the inlet opening. So you will have water coming on both directions for a sag pit. And the amount of water that comes across, it'll first start, quite shallow, and it'll sort of drop into the grate and drop into the kerb opening. But the more water that approaches, it will start to pond or fill up or submerge that whole pit itself. And so the physical dimensions that we're really concerned about is the kerb opening, the size of that kerb opening, the grate in some cases, though sometimes blockage might ignore a grate in some standards, and then the actual depth of ponding that may be achieved. So that's how we look at a sag condition. Now, this is an inlet chart. This is from Brisbane City Council. You can download these inlet charts as well for free. I can give you the link to that if anyone needs it. But the way that we use these inlet charts for a sag condition, it is different to on grade. we need to look at first the approach flow. So how much water is heading to this sag location? Now, when we're in a sag, because the water just sits there, there is no bypass flow. The water that comes across in a minor event needs to be captured and pushed underground. So our approach flow technically needs to be our inflow. We can't have any bypass. So with that in mind, what we do is we select a trial inlet type. So on this chart here, we've got three lines that you can see, or three different series. Each one of those is for a specific chart. And this comes back to my point that if you're doing pit and pipe design, you need a specific inlet chart for every specific pit type. So you select your trial inlet type, you identify the curve that you're going to use, and then you look at the approach flow. So in this case, let's say we had an approach flow of 250 liters a second heading to this pit, this sag pit. We know that our approach flow needs to be our capture flow or our inflow because it can't go anywhere else. So we read across 250 liters a second. We hit the chart that that represents the pit type that we're testing or that we think we can use. So in this case, it's a lip in line gully pit with a 2.4 meter lintel. Then you read down the chart and you'll see in this case, you'll need a ponding depth of 126 millimeters. So what does that actually mean in the real world? Well, if we have 250 liters a second heading to this sag pit, we need to make sure that we can allow that pit to actually pond or fill up 126 millimeters deep. So if we had that scenario and you needed 400 millimeters deep to actually force all that water in the pit, it's not going to work. That's too deep. It won't comply with our standards of a maximum depth, or physically it may not be possible. 400 millimeters deep or even 300 millimeters, and it's still kind of acceptable. It might build up past the curb and then past the verge and then start overtopping into someone's property. So you physically may not even be able to get up to that ponding depth. And that's where these inlet charts help us decide whether we use that pit or if we need a bigger pit to capture more flow. And then finally, we look at the on-grade conditions. So we looked at a sag pit when it's in a low point, all the water sort of ponds there. This is now an on-grade. So the performance of an on-grade pit is based, again, on the dimensions of the pit itself. So the kerb opening and also the grate. And so that will allow the water to drop into the pit and then discharge through our pipe network. But the other thing that we've got to consider as this water approaches the pit and then potentially bypasses is the road grade itself. So if you have a flat grade on your road, so maybe 1%, 2%, the water is going to be traveling a lot slower. So it gives the water a chance to actually fall into our pit. If you have a very steep road grade, the water is going to be traveling really fast, and there's a good chance you'll start to get a lot more bypass flow and not as much flow dropping into your pit. The other thing that we need to look at is the crossfall of the road. So anyone that's used Manning's equation for a little while now will understand that the deeper the flow, the more flow or the faster that velocity is going to be. So if you had a road that was very flat with, say, a 2.5% crossfall, that won't have as much water, I suppose, being able to go into that pit. Whereas if you increase the crossfall and you have a deeper amount of flow, it'll actually push more water into that pit. So they're the things that we've got to look at, the road grade and the road crossfall for on-grade inlets. So again, with the on-grade pits, we will have approach flow, we'll have inflow, but we may also have bypass flow. So that's something to consider when we start looking at these calculations. So for an on-grade pit, again, you would have specific inlet charts for specific pit types. So in this case, again, Brisbane City Council, we're using an an on-grade inlet chart, or a hydraulic capture chart is what they're called sometimes. But this is only for one specific pit. So if you've got 5 or 6 different pit types, different size lintels, different configurations of kerb openings and grates, you will need the same amount of inlet charts. So in this case, we need to select a trial pit. We don't know what pit's going to work, but we can have an educated guess. We can then identify the chart that represents that pit. And then we can read across our approach flow and then find out how much this inlet is going to capture. So we first look at the specific chart for the specific pit. So we've got that. And then all these different lines that you see here represent the different grade of the road. And so at the top, we've got a very flat grade of 0.5%, all the way down to the bottom line is 16%. And the more that you play with these calculations, you'll start to see different trends or relationships. And typically, the flatter the road, the more water your pit will capture. The steeper the road, the more bypass you will have. So let's say we had a road grade of 1%. And let's say we calculated our approach flow at 250 liters per second. So we simply just read up our approach flow until it intersects with our road grade profile. Then we read across and we find out how much water that pit will actually capture. So in this case, it will only capture 160 liters per second. So that 100% capture line, which is that 45-degree angle, that black line there, that's saying that if you have an approach flow, it will capture all of that flow. And what you can see here is there is no line that even comes close to that 100% capture unless the flows are really, really small. So that's something to keep in mind when we're doing on-grade pit design. Typically, you will always have bypass flow from your inlets. And that also has a bit of a knock-on effect, because then when you look at the pit downstream, you've got to work out the catchment of all the water heading to that pit, and then you have to add this extra bypass that occurs. So in this case, we had 250 liters a second approaching, but only 160 was captured. So that means there's 90 liters a second that we're actually letting, continuing to discharge downstream. So again, what does that look like in the real world? So we might have 250 liters a second heading towards the pit, but only 160 will fall into the pit itself and through your pipe network. So then you have this 90 liters a second that will continue on downstream. All right, so that was a bit of a crash course. I wish I had another 3 or 4 hours to elaborate, but we don't, unfortunately. But these are some of the common sort of scenarios that come up, or I guess things that you might hear around the office that maybe you don't quite understand or not confident in. So looking at custom inlet charts, if you've got different configurations or double pits or a really long trough where you've got to like sort of extend a series of kerb openings, you'll need custom inlet charts. And so a lot of people ask about that. Well, where do we even find those? And the answer is you create those. You have to do the mathematical calculations and then you produce those charts, just like what we saw from Brisbane City Council. There's various inlet configurations. So a lot of people don't quite understand the difference between gully pits and field inlets, or a big one is field inlets when they're on grade. A lot of people will put field inlets on an actual grade itself. And I can tell you right now that they do virtually nothing. You might as well just rip them out and save a bit of money and try to find out other ways to control the stormwater. Different states and territories and councils. Brisbane City Council has these hydraulic capture charts, which is great, but there's a lot of other councils and other states and territories where they don't have that data and they just don't know where to go or where to use that information. And I've got to stress, if your inlet is not exactly the same dimensions as, say, the Brisbane City Council inlet charts, you cannot use those charts. Your pit will behave differently, and then you're at risk at underestimating or not calculating your pit and pipe design correctly. Field inlets on grade, that's a big one that I always see in the industry. Blockage factors are another thing to really understand how we look at blockage and what sort of blockage factors we use. Sensitivity analysis. So what if my final pipe downstream becomes fully blocked and then all of that pit system becomes obsolete? Then what happens? And severe storm impact statements is another one as well. So again, if you're not confident or familiar with any of these, get in touch and we can teach you and we can run through either individuals or companies as well, and we can do a bit of a technical workshop. All right. Thanks so much, guys. Back to you, Brad, and hopefully we've got a few questions. And hopefully I came in around about on time.
Oh, sterling performance, Sean. And yeah, you're right. Look, we have had a lot of questions come through already. And just a reminder, if you could put your questions in the Q&A panel. Generally, it's a case of first come, first served. And I can see there's 7 already. So I'm just going to go first up was Loic Thoman asks, are grates mainly for preventing people or debris getting in?
Interesting one, that one. I'm not actually sure where the grates sort of come from. I think it's maintenance. So you can actually, pop the grate and then you've got the whole chamber there to just sort of clean it out. Because these these inlets, they will block up and pretty easily and quickly. You just need a couple half decent storms, not even a 1-year storm, even less, and you can actually get a lot of debris that fills up. I think it's more maintenance more than anything. And then you might have inlet pits that don't have the grate section, like side entry pits, but you'll have a chamber maybe behind the kerb, and that might just have a manhole lid that you can just lift up and access. But the grate itself doesn't do a lot of the capturing, if you like. It's more the kerb opening. It'll spill into that first.
Cool. Question from Neil Moodgill asks, the flow limit tables, do they come out of QDM?
The flow limit tables that we saw are QDM based. So that's a Queensland focus. But if you go to, say, the Northern Territory, they'll have their own flow limits as well. And typically, it's a bit of a balance between environmental considerations. So up in the NT, we have a massive amount of rain, very intense storms. Victoria will be very different, and Tasmania, it's a lot less in the rainfall intensity. So they'll have their own sort of limitations of what they'll use. And it depends on the council as well, what they can afford to maintain and construct and put out there. So it's a bit of a risk and practical balance.
Cool. Question from Matt Coyne asks, if your flow limits for major storms, I noticed the reference to floor levels of buildings only referenced existing buildings. Would you generally adopt the same limits for new developments in greenfield sites with high sides and low sides, or rely on or work with minimum floor level restrictions?
That's a good question. There's no exact answer. There's some councils now that are putting more of a risk-based solution. So, 10, 15, 20 years ago, what we used to do, it was very black and white. And so you needed freeboard to habitable levels. So if somebody's physically going to be living there, you need to work out your worst storm and then add an extra buffer, if you like, 300 mil, let's say. But now we're actually looking at, we're realizing it's not as black and white as that. So sometimes it is a risk-based approach, and it's almost like a balance in an engineering judgment, and that's with council standards. And they'll say you've got to assess your DV product, flood evacuation routes, how long is it going to be flooded for, where can people get in and out. So it's a bit tricky, that one. The floor levels is interesting. So one example, I know on hospitals, your floor level needs to be at or above the Q500 flood level. It doesn't mean that you need to design your pits and your pipes and your roads for a Q500 flow. It just means that when that 500-year event happens and everything floods, you've got to have your hospital sitting proud of that, obviously. So yeah, floor levels are a little bit different to actual flow limits, but they're kind of related, I suppose.
Cool. Julian Gianetti asks, in relation to the on-grade inlet condition, if you have a catchment flow of 250 litres a second and an inlet capacity of 160 litres per second, could you just install a second pit directly downstream of the pit, of this pit?
Yes.
And assume an additional 160 litres per second would be provided, therefore no bypass. So yes?
Yes, that's a good, yep, exactly. That's exactly right. And that's how we get into that whole pit and pipe design. You start placing these pits in strategic locations, testing the calculations, and then you just shuffle them around or add another pit. Yeah, spot on.
A question from Sanjeeva Rajapakse. Apologies for the pronunciation. They ask, are these flow width from Ostro's guidelines?
These flow widths or limits that we see are from QDM, but generally a lot of our standards come from OSRoads, and a lot of those standards come from AASHTO, which is an American highway sort of guideline. So once you start reading all these different guidelines, you will pick up similarities and you can kind of see where they got them from. But OSRoads will have maybe slightly different guidelines or limits. But usually what happens is OSRoads is a national guideline, so it's all of Australia. But we know those environmental conditions change quite a lot depending on where you are. So OSRoads will give you a bit of a benchmark, but then if you have your state authorities like Queensland TMR or TFNSW or Vic Roads, they might have supplementary guidelines that will have different flow limits that you might need to use. And then on top or below that, you might have local government authorities, and they might specify slightly different limits for what they want for their particular infrastructure and community as well. So you kind of got to go through national, state, and local guidelines to find those answers.
Cool. Questions are coming in quicker than poor old Sean can answer them. So we'll
Right
try. Nick Rees asks, can you do a worked example of a custom inlet chart, please? Maybe that's something that you'd have to do separate for today.
Yeah, we can, but we can definitely. Give me an hour and I'll be able to teach anyone how to create a custom inlet chart and then how to use them. So definitely reach out and then we can definitely help you out there.
Cool. Mohammed Hira asks, for sag inlets, do we need to consider any reverse flow in rational method, or is it truly a dynamic method?
So by reverse flow, I'm assuming you mean backwater effect. So the water's going to pond up. Yeah, it's a good question. So the rational method or your pit and pipe design does not take into consideration backwater effect. If you're worried about backwater and you think that's going to occur, you've got to throw rational method out completely. And then you use a different type of hydrological method, if you like. So it might be a time area method, like ILSACs, or it might be initial loss, continuing loss. And that's where you start to look at actual storms. So you'll have a hydrograph where the water will kind of peak over time and then drop back off. And that's a little bit more, I won't say complicated, like it's not hard once you know it, but there's just a few more steps involved. And obviously the computer software helps us out as well. But yeah, if you are worried about that, you've got to go past and beyond the rational method.
Cool. Dev Krishnasamy, sorry for these mispronunciations. They ask for a link to the inlet charts. I guess you just have to contact Sean directly for that. Yeah. Igmar Zambrano asks, has the current weather events impacted the inlet calculation limits, e.g. DVE flow depth?
Yeah, that's a good one. Look, eventually they will. Guidelines will eventually catch up. But the problem with a lot of our planning scheme policies or development control plans, they're written at a certain point in time. So, it might be sort of 2015, say, that they wrote these guidelines, and we're still using them now, 10 years later, and then they'll be revised. So we're using old standards and guidelines and practices, and that's the best that we had at the time. So not to be critical on that, it is what it is. The events that we're seeing, obviously the effect of climate change, it's really making us sort of sit up and listen and figure out how we're going to assess the unpredictable nature of what we're actually seeing. So in an ideal world, yes, every year, every 5 years, we would look at all these storms and say, hey, these storm frequencies, they're happening a lot more frequent than we actually thought they would. And so ideally, the next day you would change those guidelines and you would update your I guess your benchmarks that you're trying to design to. But we know that's impossible. We can't do that. So eventually, like I guarantee you, the next Brisbane City Council planning scheme policy will have a lot more climate change data in there. Sunny Coast Regional Council is doing a great job. They've implemented climate change factors on rainfall intensities. So they're actually seeing all the science and research, and they're acting quickly because they know they want to keep their community, their council area, they want to keep everyone safe. Yeah.
Cool. Another request for the Excel spreadsheet. I think if you've got any requests for spreadsheets, tools,
Yes,
links,
send
charts,
me a link
just send
or
them
an
through
email
to,
or
yeah.
yeah.
There's been a few of those, so I might just have to bundle them up together. Um, uh, Gopal Nupane asks, I've seen some councils' new development sites in SEQ have all property connection discharged into the curb by adapters rather than connecting into the pipe system. Do you have any comments on the practice there? Gopal's
Yeah,
curious.
that's standard practice. And so if you're looking at curb adapters, typically that's just the roof area that you're looking at. So if we look at a residential house, all your roofs connected with downpipes, and then you'll have a single, usually like a 150 that will go out to the verge, and then you'll have a curb adapter, like 100 or 90 mil sort of diameter that will break out into the curb and allow that water to go through. But there are limitations. You can only have a certain amount of flow discharge onto the road. So you can't have a heap of water just gushing out. I've seen some dodgy practice, especially in industrial areas where you might have, 5 or 6, curb adapters. And I've even seen some where they've got like a 225 that runs over the footpath or just stops at the footpath and all this water just gushes out. So you've got to watch out for sort of dodgy practices, I suppose. But there's limitations. If you've got too much water that's discharging out of that curb adapter, and you will need to calculate that. You need to be confident on every curb adapter how much water is discharging. If there's too much, then you need to pipe that somewhere and put it under the ground and not let it spill out onto the road.
Question from Ezra asks if they can't find the appropriate inlet capture charts, what should they do?
That's where you'll create your own inlet capture
Mhm.
charts. So there's a few mathematical equations that you can use. I can point you to HEC 22, which is the what is it? Highway Engineering Circular 22. It's a guideline that's used in the US, and they've got a heap of different equations that you kind of pin together, and it's based on your curb opening, the throat distance, the grades, the grates, the blockage factors, and it'll work out how much water that pit will capture at certain depths or grades. And from that, you'll be able to build up basically a table with a series of data, and that's what you'll push into an inlet chart. But again, I'm more than happy to help out. If anyone needs that, we can organize a workshop or just a quick catch up over Teams and do that as well.
You're a busy man, Sean. I don't know how you do it all. A question from Zeno Wu asks, I believe the grate needs to be configured if we have a new product. However, I cannot find any inflow or outflow data for grates from suppliers. What is the best practice in this case?
Yeah, that's a good one. That's interesting, actually. And actually the image that we've got when you join the webinar, you might have seen the grate and the water splashing over. And so, as I do, when it pours down rain, I'm always running around taking photos and looking and trying to link it back to all the maths that I've been calculating. That's what we call splash over velocity, or the limitations of a particular grate. And so if you've got grates that have longitudinal bars and the water's going in this direction, it's generally going to drop in nice and easily. If you've got transverse bars, the water's going to come and kind of hit it and bounce and splash and do all sorts of things. And then you've got a combination where they're both longitudinal, transverse, and then you have proprietary products where you have trying to think what the name was, Manflow, I think it was, MANN, like Manning's Flow or something. And they've actually got veins, like it's sort of, rather than a bar, it's actually shaped like this all the way through the grate. So it's meant to sort of push and funnel the water into the grate quicker. Um, I mean, they do make some sort of a difference, but I don't know if it's enough to sort of warrant, it's going to save your design necessarily. And the other thing is a lot of the time with grates, you've got to account for some blockage of a grate as well, whether it's on grade or in sag. So sometimes those sort of slight differences in calculations won't really make too much difference. Yeah.
Cool. Ben Wolfgram asks, curb inlet pit inserts will impact capacity. I guess
Yeah.
suppliers will provide advice on this.
That's interesting. And that hasn't really popped up in the
Mm.
industry, but it's something that I've thought about as well. Yeah, that's right. If you've got that insert, it may affect it. But I think it comes down to two things. First, with the inserts, so the litter basket, if you like, when it sits in there, there is actually a weir all the way around So even if that was full of rubbish and gross pollutants, it will also allow that water to bypass. And that's been designed, and a lot of thought and calculations have gone into that. So I don't think it'll affect it too much in that case. But if you don't maintain these things, that's when it becomes a problem. If those litter baskets aren't emptied and all those pollutants aren't removed, and then the next storm hits and another one, and like 3 or 4 years later, you're just going to get this brick of just rubbish that's sitting there, and that may start to fill up near the weir and cause some issues.
Yeah, cool. Question from Moen asks, how can you go about creating custom inlet charts? When adopting council standard drawings, GSEP and council and manufacturers don't have information on inlet charts. Are you able to provide resources where this can be calculated?
Yeah, again, HEC 22 is a good one to start, and that's got all the mathematical equations that you need to calculate that. But then I can definitely help out as well. And if you're looking at inlet charts, I will say, if you have testing data, if someone's physically done some laboratory tests and they've got results, that's the most reliable data that you can get, in my opinion, because someone's physically seen what happens. The mathematical equations are a good estimate of what we think might happen. So just keep that in mind. If you have calculated inlet charts and then someone does some testing, I'd be going for the testing more than the theoretical calculations. And on top of that, if you're ever unsure, or if you got the calculations and it's like razor thin on whether it will work or not work, that's when I do these sensitivity analysis and just say, well, what if that pit's taken out of the equation completely? Then what happens? And if no one's going to die or drown, or properties aren't going to be severely impacted and flooded, then you're probably okay.
Cool. Question from Thomas Steinthal. Generally, if you're designing on a greenfield project, will you collaborate with the civil designers producing the road and lot grades to optimize the stormwater design, or will you the stormwater design / pit and pipe network be detailed once civil design is set?
This is a great question. This is my opinion, but if you're designing a road, you need to understand stormwater. And if you're designing stormwater pit and pipe, you need to understand road geometry. They're not separate elements. They're not separate engineering fields. You need to be across both. And the reason why I say that is if I'm designing a road and I know the road's coming down to a sag, as I'm designing that sag, I'm thinking about the stormwater and saying, well, the water's going to pond there. I'm definitely going to need pit and pipe design. Or depending on what sort of development, I might need a box culvert underneath there. So you're constantly thinking about that. And then if I go to put in that culvert, I'm going to be spatially thinking about, well, if that culvert's going to go through, I know my road's here, but I've also got a pavement depth. So I'm thinking about the pavement sizing and thickness of the material. And then I've got subsoil drainage coming through there. So all these different elements, when you're designing a road, you've got to be across all of it, in my opinion. There's no two ways around it. And if you're not, it's not the end of the world. It just means that you're going to be a lot more inefficient. You'll spend a lot more time getting your design and then handing it to somebody else. They'll look at the stormwater analysis and say, you idiot, you forgot all this stuff. Go and change your road design. And you just bounce back and forth. And some, especially sort of larger companies, you tend to get that sort of siloed effect. And it's something that we do try to avoid, but it does come up. But yeah, to answer your question, you need to be across both to do that.
Question from Bennett James Valencia asks, do you have any insights in utilizing anti-ponding pits along areas where sag locations are on kerb returns?
Anti-ponding pits are like a last resort. So if you end up having, say, a kerb return and there's a slight depression somewhere in there, you can put in an anti-ponding pit, which is basically just a grated inlet. There's no kerb opening. The problem with those, because it's in a sag and it's just the grate that we're relying on, they will block up pretty quickly and pretty easily. So if your design is relying on one of these pits, that's a pretty risky move, in my opinion. And sometimes they can't be avoided. And again, to come back to the previous question, if you're designing that road and you're thinking about the stormwater as well, and you get a kerb return with one of these trouble sort of shallow depressions, that's when you can stop, revisit your road design and actually regrade it to push that sag out completely, get an on grade, or push that sag a little bit beyond the kerb return to the tangent point, and then have a proper sag inlet with the kerb opening. So
Cool.
yeah, a lot of things to sort of juggle and bounce around, but that's how I would approach it.
And for everyone dialing still with us, there's 250 people still here. But hang on every word that Sean is sharing. But look, we might pull the pin on questions. I've got 4 more to go. Unless you've got a really burning question, please do it. Put it in now. But if you don't, obviously, please reach out to Sean, and obviously his contact details here. But Darren's been very patient. Darren Miller asks, based on the 2016 AR&R rainfall data being out of date somewhat, now with climate change, would it be more efficient to just upsize the minor storm event from 5 to 10, etc.? Or is that more an industry practice discussion?
Yeah, that's a good one. And in fact, we touched on this on the Quilty Engineering Hub newsletter that just came out a couple of days ago. So if you haven't subscribed, definitely jump on. You'll get all this useful info. But on the front of that newsletter, it actually talked about this. It talked about climate change and how climate change is affecting rainfall intensity. And that directly goes and affects our rational method, which then affects our pit and pipe design. So there's 2 parts there. There's rainfall intensity, and then there's the storm frequency. So the AR&R data that we find, they do say 2016, but I believe that data is live. It's constantly being updated with all the storms that are actually occurring. And so in 12 months' time, your data will be slightly different because we'll have another 12 months of pluviograph data that they're pushing in there and doing all the statistical analysis to give us our IFD tables. So the storm frequency, as far as I can see in the industry, that's not really changing, and I think it probably should as well. I think we need to reassess whether a 1% storm is truly 1% chance, or is it now double the chance of happening in any year. But climate change definitely does affect rainfall intensity, and we've even seen locally in Australia, we're in an El Nino weather pattern. And that does not mean that we're just in for droughts and no rain. There's a lot of other factors that come into it. And we've even seen recently, it's meant to be this dry sort of period, but we've had some of the most severe, intense storm events that we've seen in as long as we've been basically recording this history. So yeah, a good question, good to look at. And on that newsletter, it talks about how that rainfall intensity increases, but there's a climate change factor that you can apply to your rainfall intensities. And then that will give you at least some way of incorporating climate change into your pit and pipe design.
Cool. Ajaya, I think, asks, are these inlet pits all designed for just minor flows?
Good question. Typically, yes. Typically, we want to rely on the pit and pipe system just for these minor events. And the reason why is they can become blocked. And not just at each individual pit, but you might have maybe a really large opening somewhere down the line. And if a whole heap of rubbish or whatever gets in there and actually blocks a pipe, then that whole upstream network is now useless. It'll just fill up very quickly, and then you're not getting any of release through that pipe system. So in good practice, we do want to limit that just purely to the minor event. You do want to do a sensitivity analysis. What if one of those or all those pits and pipes are just completely blocked or not used? Then what happens? But there's always scenarios where it doesn't follow the rule book, I suppose, and that's where you may have to pipe your major events or events larger than your minor events. And I've had quite a few jobs where we've had to do that up in Darwin, Southeast Queensland, North Queensland, where we need to there's no other way to push this water. Another thing that happens is in brownfield sites. So if you're in the CBD or whatever, there's a lot of infrastructure around you. It's not greenfield. It's not just an open paddock that you can put a new subdivision on. You will have limitations there, and you may not physically get the levels to actually allow overland flow to escape. And in that case, you might have to capture your Q100 event. But if you do come into that scenario, again, I'm always open to sort of talk it through or give you a bit of advice from the theory side of things. There's things or measures that we can put in place to try and pipe that Q100 event. And if blockage happens, we might have redundancy in our system or other pits strategically placed to allow for that what if scenario.
One final we might have to wrap it up after this question, Sean. So no, and again, apologies, I haven't got through to everyone's questions. But I'll leave the last question to Shenyu. Asks, They've seen some experimental data to indicate that the inclusion of deflectors in pits can significantly improve the intake flows, especially on steep grades. Is this analysis part of Brisbane's inlet capacity calculations?
I haven't seen that particular research, and I'd love to see it. If you want to flick it through to me, I'd love to have a bit of a read. The inlet charts that we have for Brisbane City Council do not incorporate deflectors. I know City of Darwin use deflectors on their side entry pits. So when they have inlet charts, that will actually, if it's tested, if they do testing, laboratory testing, it will incorporate it because you'll physically have those deflectors. HEC 22, the mathematical calculations will not account for deflectors. So I think either you do laboratory testing, which could be pretty expensive, or something that's just starting to sort of come around now is CFD modeling. So what is that? Continuous fluid dynamics. I don't know. I'll probably stuff that up. But it essentially, it uses computer software, and there's a lot of processing that needs to go on, but you'll actually physically see where the water is going to go in all different sort of shapes. Very accurate, very detailed, but pretty sort of time consuming. You might be able to physically model the pit with the deflectors, run flows through there, and then you can get inlet charts out of those possibly. But yeah, really interested in that research if you flick it through.
We might have to cut it up there, Sean. A lot of people are still asking about questions and trying to get your thoughts on your favorite books about stormwater and charts. And just a reminder, the recording and the slides will be made available on the Ocean Protect website before tomorrow morning. If you're interested in coming along to tomorrow's webinar, the link for that to register for that is also at oceanprotect.com.au/webinars. Again, if you need a CPD form, I've also included a link to the email address to send that to in the chat as well. But look, on behalf of everyone who's dialed in, and I think at one stage we had about 450 people in attendance. So I think this has just pipped the most popular webinar of all time about inlet design. Can you believe it?
It's probably the first about inlet design.
Yeah, that's true. But look, on behalf of everyone in attendance, Sean, thank you so much for giving up your time and energy. It was another wonderful, very well received prezzo. A lot of positive feedback. And if you want to shower Sean with praise and talk about how wonderful he is, feel free to email him directly or reach out to him on LinkedIn. Obviously, a lot of requests for charts and spreadsheets and tools and advice. So if you want to reach out to Sean, I'm sure he'd love to talk to you about stormwater. Thanks for everyone who's dialed in as well today. Much appreciated. Certainly awesome to see so many people have so much interest in these sessions, including today's. Without further ado, enjoy the rest of your day. And again, big thanks to Sean for giving up his time, and looking forward to the next one. What's the next one, Sean?
Pipe design. So we've got
Woo!
rational method, water coming down. Inlet design, we know the water's going in the ground. Now we need to figure out how big do those pipes need to be to get that water away.
Yeah, and cool. Again, the link to register for that is under the oceanprotect.com.au/webinars page as well. So if you haven't already, please make sure you register for that if you're keen to learn all about pipe design. And who wouldn't? I mean,
who wouldn't? Thanks, Brad.
Cool. Enjoy the rest of your day, guys. Be good.